Yusra, am I audible? Okay. So let me start with fluid or hydrodynamics of fluid so that you may join batch. Okay. So in a hydrodynamics part, we first start with Newton's law of viscosity. According to Newton, liquid flows always in layer by layer, whether it will be flowing in a tube, in any canal or anything. It always flows in layer by layer structure. Suppose one of the layers will be this, its adjacent layer neighboring to it will be this, and so on. So each layer tend to oppose its neighboring layer by an opposing force, which is called viscous force, due to which there will be change in velocity between each layer of liquid. So let's say this particular layer moving at some velocity v. So this may move with some velocity v plus dv. So this upper layer will applying some opposing force to its neighboring along this direction by some opposing force, which is called viscous force. So according to Newton, each consecutive layer opposes its neighboring layer by a force which is called viscous force, which depend upon two factors. First is area of this particular layer, A, and second is, since there is change in velocity between two layers and there will be some width in between them, let's say dy. So in physics, we mainly define two different terms. First is rate. You must have learned about rate in chapter number 3. Krishna, any idea? Suppose if a quantity is changing with respect to time, we can call it as rate of change in that particular quantity. So change in a quantity or any physical quantity with respect to time is called rate. Similarly, there is another term that is called gradient. Change in quantity with respect to length is called gradient. So in this part, there is change in velocity as this layer is moving with some velocity v, this upper layer having velocity v plus dv. So there is extra velocity of this particular upper layer, and this particular change in velocity between two layers is with respect to this width of layer. So we can call it as velocity gradient. Is it clear?
Yes, sir.
Yes, sir.
Okay. So according to Newton's law of viscosity, let me define you its statement. Liquid flows in layer by layer structure in which each layer opposes its neighboring by a force called viscous force, which depends upon or which is directly proportional to the area of liquid film and also to the velocity gradient. So according to this relation, we can write viscous force is proportional to area of this liquid layer, and also it is directly proportional to the velocity gradient, means change in velocity with respect to width. So if you combine these two terms, you'll get Fv proportional to A dV by dy. Just replace this particular proportionality sign by any constant term. So here it will be Fv equals to eta A dV by dy, and with some negative sign, since this particular viscous force is opposing in nature. So this particular constant of proportionality is called coefficient of viscosity. Having SI unit, Pascal second, CGS unit, poise, and there is a relation in between these two terms. 1 Pascal second is equals to 10 poise. Yusra, do you have any doubt to this part?
No, sir.
Krishna?
No, sir.
Okay, just write it down to this part. Krishna, you have written?
Yes, sir. Done, sir.
Yusra?
Yes, sir.
Now, this particular coefficient of viscosity, eta, may depend upon certain factor. First is eta depends upon nature of liquid. So it may have different value for different liquid. And next is temperature. Let me define you how it will relate it with temperature. Suppose if you increase the temperature of that particular liquid, so on increasing temperature, bond gets weakened, or you can say particle of that particular liquid or that matter may acquire some thermal kinetic energy, due to which they will tend to move faster So the opposing force in between them decreases. So eta is inversely proportional with a rise in temperature. Okay. Krishna, is it
Yes,
clear?
sir.
Okay. Next, we can define this particular coefficient of viscosity in some other relation as well. Suppose we had this particular layer of liquid, which is going along this direction. So it must have applied some opposing force to its neighboring layer along this direction. So we may treat this particular force tangential to the surface. And this force acting this surface tangentially per unit area may be defined as shear stress. So shear stress is force that is tangentially acting on that surface per unit area. Next, this particular layer having velocity v plus dv, and there is change in this particular layer having width dy. So I defined this particular change in velocity divided by dy as velocity gradient. We can also write it as dv by dy equals to velocity is length per unit time. This particular term dx is along horizontal shift, or you can say this is horizontal shift, divided by dy, which is vertical length. So this particular ratio is also called strain. These are some terms from last chapter, that is mechanical properties of solid, which I will define you later. And this particular term, that is time taken. So any quantity divided by time taken may be called as rate. So we can call this particular ratio as strain rate. So related to these two terms, we can write coefficient of viscosity equals to F divided by A whole divided by dV over dy. This numerator is nothing but shear stress, and this denominator is nothing but strain rate. So coefficient of viscosity is also equals to the ratio of shear stress and strain rate. Is it clear?
Yes,
Yes,
sir.
sir.
Okay, just write it down. You both have written?
1 minute, sir. Done, sir.
Krishna, you have written?
Yes, sir, done, sir.
Okay. Now, on the basis of this viscosity, we may define types of flow of liquid in different tube. So next is types of flow of liquid. Suppose there is a tube having variable cross section. Area at this point is A1, area at this point is A2. If velocity of each layer of liquid at this instant is V1, velocity of each layer of liquid at this instant is V2. This particular flow could be possible only if there is no viscosity between layer of liquid. So we can say this flow would be possible if liquid is non-viscous and it should be incompressible and should be irrotational. So it is non-viscous, incompressible, and irrotational. Then this particular flow would be possible so that each layer at a particular instant will move with same velocity. So this particular flow of liquid is called streamline and is also called ideal flow. In which velocity of each layer at a given instant is same. Yusra, is it clear?
Yes, sir.
Now suppose there is a tube having uniform cross-sectional area and there is some viscosity in between each layer. So centralmost layer will move with maximum velocity and all its adjacent layer will experience some opposing force due to its neighboring layer as well as due to the side wall of that particular tube. So it may get lesser velocity as compared to the central part. So in this, each layer having different velocity due to opposition by adjacent layer as well as side wall. So this particular flow of liquid is called laminar flow. Krishna, is it clear?
Yes, sir.
Now there is third type of flow. Suppose there is a tube in which each layer having irregular velocity or uneven velocity. This particular layer will moving with some velocity v. This adjacent layer may move with some greater velocity. Or you can say, if there is obstacle in this particular path for this middle layer liquid, let's say at this point. So on striking with this obstacle, this layer would get stopped at this instant. So it will create a vacant space at this point after it. So this layer on moving forward may experience inward force and may get spiraled like this. Similarly, this layer may get spiraled at this point So this particular flow in which there is formation of eddies is called turbulent flow. So if each layer having uneven or irregular velocity, so they may get spiraled and form eddies. This type of flow is called turbulent flow. So we mainly have these three different types of flow of liquid, in which first one is ideal flow, which is also called streamline, in which it should be possible only if liquid should be non-viscous, incompressible, and irrotational. Yusra, do you have any doubt till this part?
No, sir. So can you read the red part in the first streamline flow?
Velocity of each layer at a given instant is same.
Okay, sir. Thank
Suppose
you.
you are considering this particular instant. So at that instant, each layer will move with same velocity as there is no viscosity in between them. Both have written?
So just 1 second, sir. Done, sir.
Yusra, done?
Yes, sir.
Okay. So let's stop here for a while. I'm just continuing with the rest of the strength, okay? Just 2-minute break, okay? Hello. Asma, do you have any doubt from last class?
No, sir, no doubt.
Okay. So in last class, we had defined Stokes' law in hydrodynamics. Okay, next is application related to that viscosity. So you'll have to define terminal velocity. Suppose there is a body having radius r. If initially it is dropped in a viscous medium, so on moving to some distance, let's say to this point, it may have acquired some velocity due to falling down under the effect of gravity. So on attaining some velocity, it may experience some viscous force due to Stokes' law in opposite direction of its motion. Suppose it is moving along this direction at some velocity v. So viscous force must be acting opposite to it, let's say along this direction. Since it is moving under the effect of gravity, so there will be a force acting along downward direction that will be due to its weight. And since it is surrounded by any fluid, so it must have displaced some of its volume. So it may experience an upward force, which is called buoyant force. So in general, this particular object in this viscous medium is capable of experiencing these number of forces. And if net force acting on this particular body at this instant becomes zero, then it will move with some constant velocity in this viscous medium. That constant velocity with which a body moves in a viscous medium is called terminal velocity. Is it clear? Let me explain you again. Suppose there is a body which is initially dropped in a viscous medium or may projected with some velocity u. So on moving down, it may have acquired some velocity v. So due to this velocity, there will be some viscous force experienced on it on attaining this much amount of velocity in opposite direction. Next, since it is acted upon by gravity, so must be experiencing weight in downward direction or towards gravity. Next, since it is surrounded by any liquid, so it must have displaced some of its volume. So due to that displacement of volume, it may experience some buoyant force in opposite of weight. So at this instant, this object is experiencing buoyant force and weight. Now suppose net force acting on this body at this instant becomes zero. Then it will start with move with some constant velocity. This constant velocity is called terminal velocity. Asma, is it clear? Samara?
Yes, sir.
So we can define this terminal velocity as the constant velocity with which body ascend or descend in viscous medium is called terminal velocity. Now, since velocity is constant, so constant velocity will have zero acceleration. So acceleration of this particular body will be zero. It means net force experiencing on it must be zero. Now we have three different forces acting on this particular object, two in upward direction and one in downward direction. So total upward force and total downward force should be equal to each other. Now put the value of each part. Viscous force is 6 pi eta r times b. Buoyant force is density of medium times volume of object times gravity. Weight of object is mass times gravity. We can write mass in terms of density as density of object into volume times gravity. Now move this term to right side. So you're left with 6 pi eta r times v equals to sigma minus rho times 4 by 3 pi r cube times g. Now move this 6 pi eta r to right side. So you're left with velocity equals to 2 times r square by 9 times eta bracket sigma minus rho times g. So this will be your expression of calculating terminal velocity related with radius, density, and coefficient of viscosity. Yusra, is it clear?
Yes, sir.
Krishna, any doubt?
No, sir.
Okay. Just write it down. Then I'm defining its various application.
Done, sir.
Done, sir.
Yusra, you have written?
Yes, sir.
Krishna, done?
Yes, sir.
Okay. Now, this particular velocity, which I have derived, is in terms of radius and eta and gravity, like this. There will be another expression of terminal velocity in terms of mass as well. So we can write viscous force plus buoyant force equals to weight. Viscous force is 6 pi eta r times velocity. Buoyant force is density of object times volume displaced times gravity. Weight equals to density of object times volume times gravity. So move this term to the right side. So you're left with 6 pi eta r times v equals to sigma vg minus rho vg. Just take out sigma volume gravity to be common. So you're left with 1 minus rho divided by sigma. Now this sigma times volume is mass. So we can write mass times gravity. Move this 6 pi eta to right side. So it will be 6 pi eta r bracket 1 minus rho by sigma equals to terminal velocity. So this is another expression of getting terminal velocity in terms of mass. So if there is question in terms of radius only, so just use the above formula. And if there is relation in terms of mass, so just use this formula. Samaira, is it clear?
Yes, sir.
Okay. Now, there will be question related to graph for this terminal velocity. As terminal velocity is a constant value, let's say this constant velocity is this much. So if a body is dropped in a viscous medium, so it may follow this curve to attain terminal velocity at some time or at some height. In this, initial velocity of object is 0. In some other case, suppose if a body is projected with some initial velocity which is lesser as compared to terminal velocity, so it may acquire terminal velocity at some other distance instant like this. So in this, u is less than terminal velocity but greater than 0. Now suppose if a body is projected at some greater velocity as compared to terminal velocity, so its velocity start decreasing to attain terminal velocity at any instant like this. So this horizontal corresponding will be with respect to time or with respect to height. So in all of the three cases, at some later instant, it will obtain or attain terminal velocity due to viscous force experiencing on it. Is it clear?
Yes, sir.
Now, depending upon the value of density of object and density of medium, we may define its different behavior. Suppose density of object is greater as compared to density of medium. So this particular ratio will be smaller as compared to 1. So terminal velocity in this case will be positive. It means object will descend in that viscous medium. Suppose sigma is equals to rho. So this ratio will become 1. So 1 minus 1 will be 0. So terminal velocity in this case will be 0. That there is no upliftment or down fall, or there will be no ascending or descending. It will remain at rest in equilibrium at its own position. And third part, if sigma is less as compared to rho, that is surrounding medium, so terminal velocity will become negative. So it will start ascending. Krishna, is it clear?
Yes, sir.
Asma, any doubt?
No, sir, no doubt.
Okay.
Done, sir.
You all have written?
Yes,
Yes,
sir.
sir.
Okay. If air bubble having radius 2 mm in water having coefficient of viscosity 0.05 Pascal second. Find terminal velocity attained by it. Density of water is 1000 kg per meter cube and density of air is 1.3 kg per meter cube. So you may neglect this sigma as compared to rho, since rho is 1000 and sigma is just 1.3. So you can write sigma is very, very small as compared to rho. So sigma will be neglected in this case. Now put all the values in the above formula, which I had defined in terms of radius only, and I try to simplify it. Samara, you got any answer?
Sir, I'm doing.
Okay. Radius is 2 mm. So just convert it into meter. So it will be 2 × 10⁻³ meter. Take gravity to be 10. Rho is given, sigma is given. Eta is 0.05. So terminal velocity equals to 2 times r square by 9 times eta bracket sigma minus rho times gravity. This sigma is very small as compared to rho, so we can neglect it. So this will become minus of 2 times r square rho times gravity by 9 times eta. Just put all the values and simplify it. Minus of 2 r square is 4 × 10⁻⁻6. Density is 10⁻³ gravity is 10. Divide by 9 times 0.05. So if you remove this decimal, there will be 100 or 10⁻² in numerator. This 5 will cancel out this 10 in 2 times. So 2 × 4, 8, × 2, 16. Divide by 9 with negative sign into 10⁻³ plus 3 plus 2 plus 5 minus 6. So it will be minus 1. 16 by 9 will be 1.7078 into 10⁻⁻1, or you may write it as 0.17 meter per second. Asma, is it clear? Yusra?
Yes, sir.
Okay. Samaira, any doubt?
No, sir.
Okay. Now there will be some problem related to combination of draw. Suppose you have n number of small draw, each having radius r, and they are falling with some terminal velocity v1. So if they combine to form single large draw, so what will be their terminal velocity on combining? So we have to calculate v2 in terms of v1. So in this part, as velocity or terminal velocity for a particular particle is 2 times r square divided by 9 times eta bracket sigma minus rho times gravity. So gravity will remain same. Density of surrounding and density of object will also remain same. Eta, that is coefficient of viscosity of that particular drop, will remain same. So on combining, there will be change in radius of drop only. So we have to relate in somehow radius of these two different combinations. So on going from these small drop to form single large drop, there will be volume initial equals to volume final. Each small drop being spherical in shape, so it will have volume 4 by 3 pi r cube. And since there are n number of drops, so just multiply it by n equals to 4 by 3 pi r cube single large drop. So 4 by 3 pi will cancel out. So r will equals to n to the power 1 by 3 times small r. So this is relation between radius for two different combination. Now from this relation we can write V1 divided by V2 equals to R1 squared divided by R2 squared, as the rest of the term is constant, so they will cancel out each other. So we can write it as R1 over R2 whole squared. R1 is small r and R2 is n to the power 1 by 3 times of r whole squared. So this r and this r will cancel out. So you're left with n to the power 2 by 3. Now just cross multiply. You'll get V2 equals to n to the power 2 by 3 times V1. So this will be a final expression of calculating V2 in terms of V1. Samira, is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Done, sir.
Krishna, you have written.
Yes, sir. Done.
Asma, done.
Yes, sir. Done.
Okay. Now there will be a question. If raindrops are falling at 2 mm per second, if 8 of them combines to form single drop, find its terminal velocity. Try to find. In this question, we have V1 as 2 mm per second. Number of drop is 8. So we have to calculate V2. Just use the above formula and simplify it. Good, Samira. Good, Krishna. Asma, you got any answer?
So you call
Yusra?
me?
Yes. You got any answer?
I'm doing it, sir.
Suppose if you put all the values in this part, it will be V2 equals to n, which is 8 to the power 2 by 3 times V1, which is 2. So for this particular exponential, we may write 8 at 2 to the power 3. Power raised to power will get multiplied. So it will be 2 raised to 3 to the power 2 by 3. So this term and this term will cancel out. So you're left with 2 to the power 2 only. That will be 4. So this will become 4 into 2. That will be 8 mm per second. Is it clear? Yusra? Okay. Asma, any doubt till this part?
No, sir, no doubt.
Okay. Now, next topic related to this is equation of continuity. Suppose you have a tube of variable cross section. Area of cross section at this point is A1. Area of cross section at this point is A2. And which non-viscous incompressible liquid is flowing. Since this liquid is non-viscous, so each layer will move with same velocity, let's say V1. And at this point, velocity of each layer of liquid will be same, that will be V2. So we have to calculate relation between area and corresponding velocity of layer of liquid at that instant. So equation of continuity mainly defines you how rate of velocity of liquid is defined for a particular flow when liquid is non-viscous, incompressible. So it states for non-viscous, incompressible liquid in a tube, the rate of flow of liquid at any instant will be constant. I will define you what do you mean by rate of flow of liquid. Let me prove this particular statement. Suppose at this first end, liquid is entering. So we can write mass of liquid entering per unit time. As mass is related with density, mass equals to density into volume. So we can write density into volume divided by time taken. Density is rho. Volume at this first end will be equals to area of cross section times length divided by time taken. Now this x1 per unit time will be displacement divided by time or distance divided by time. We can write it as velocity. So this will be rho a1 v1. Let's say this is equation first. Samaira, is it clear?
Yes, sir.
Similarly, we can write mass of liquid ejecting per unit time equals to density into area of cross section times velocity. Let's say this is equation 2. Now, according to conservation of matter, the amount of liquid entering at this particular end, this first end, must be equal to the amount of liquid ejecting out at this other end. So we can write, according to conservation of mass, mass of liquid entering per unit time will be equal to mass of liquid ejecting per unit time. Now put the value of these two terms, what we get an equation first and second. So rho E1 V1 equals to rho E2 V2. Rho is same, so this will cancel out. So you're left with E1 V1 equals to E2 V2. Asma, is it clear? Aisha?
Yes, sir, it's clear.
Yes,
Okay.
sir.
Now, we can define rate of flow of liquid. Rate of flow of liquid is also equals to volume of liquid flowing per unit time. We can write volume as area into length divided by time t. So this particular length per unit time is also called velocity. So this product of area corresponding to velocity is called rate of flow of liquid, which is represented by Q, which is same what we have derived above. So from this we can write Q equals to area of cross section into velocity will be constant at any instant for the flow of non-viscous and incompressible liquid. Krishna, is it clear?
Yes, sir.
Okay, first write it down.
So can you please scroll down?
Done, sir.
Asma, you have written?
Yes, sir, I've written.
Okay. Suppose there is a tube this having area of cross section A through which liquid is entering at 4 meter per second. This having area of cross section 2A through which liquid is flowing at 3 meter per second. Now at this end, we have some hole. Let's say number of hole is 10, each having area A by 4. So you have to calculate, find velocity of ejection of liquid. Let me define you how to approach this problem. First, just consider according to conservation of mass, total mass of liquid entering into this particular tube must be equals to total mass of liquid ejecting out at same rate. So we have two different arms in left hand side through which liquid is entering into this particular tube. So we can write A1 V1, A2 V2, and both or through both of these two tube, liquid is entering into this particular channel. So we can add these two together. Must equals to n number of small holes, each having area A3 and velocity V3. Now put the value of each term and simplify it to find V3. Is it clear?
Yes, sir.
Okay. Good, Krishna. Suppose in this part, let's say this particular term or this particular arm to be first. So area A, velocity is 4. This is second arm. So area is 2A, velocity is 3. Equals to, we have 10 holes, each having area A by 4 times V3. So 4A plus 3 into 2, 6A equals to 10A divided by 4 times V3. So this will be 10A equals to 10A by 4 times V3. 10A and 10A will cancel out. So V3 equals to 4 meter per second. Is it clear?
Yes, sir.
Asma, any doubt?
No doubt, sir.
Okay. You all have written?
Yes, yes.
Now, related to this part, there will be a conceptual question. Suppose there is a tap at some height. So if you open this particular tap, liquid or water may fall like this. So question is, on falling down, why width of stream of this liquid is continuously shrinking? Why width of stream of water decreases on falling? Krishna, any idea?
No, sir.
Samira, any guess?
Don't know, sir.
You must have experienced this particular type of flow in everyday life. Okay, let me define you. Yusra, do you want to answer?
I don't know.
Just suppose this is initial level of liquid. At any instant, it will be at this point, and some other instant, it will be at this point. Now just consider this particular flow of liquid as free falling particle. So as it descends from this point to this point, height will be h1. On going from this point to this point, height will be h2. So according to third equation of motion for free falling body, we can write v square equals to u square plus 2gh. Let's say initial velocity be 0. So velocity equals to root under 2gh. So as it falls down, greater the height it will descend, it will attain greater velocity. And according to equation of continuity, if velocity increases, area must be decreases. That's why width of a stream on falling down get continuously shrinking. Is it clear?
Yes, sir.
Yes, sir.
So you can write as water descend, velocity increases with increase in h. So according to equation of continuity, area times velocity should be constant. Area must decreases. Hence, width of stream decreases. Asma, is it clear?
Done, sir.
Done, sir. Done, sir.
Krishna, you have written?
Yes, sir. Done, sir.
So this is all about equation of continuity. Next and the most important part of this entire chapter is Bernoulli's principle. Suppose you have a tube of varying cross section and whose end are at different level. Let's say this having area A1, area A2. This is horizontal level in which non-viscous and incompressible liquid is flowing. So velocity of liquid at this instant is V1. And velocity of liquid at this instant, let's say V2. Since they are at different level, so height of this point from ground, let's say H1, and height of this point from ground is H2. So according to Bernoulli's principle, the sum of pressure, kinetic energy per unit volume, potential energy per unit volume for the flow of non-viscous incompressible liquid at any instant should be always constant. So let me define the statement of this particular Bernoulli's principle. It states for non-viscous incompressible liquid flowing in tube, the sum of pressure, kinetic energy per unit volume, potential energy per unit volume at any instant will remain same. So first is there is some limitation of it. First draw till this part, then I'm defining the next part of it.
Done, sir.
Done, sir.
Krishna, you have written.
Yes, sir. Finish. Done, sir.
So there is some limitation of this particular principle. First is liquid should be non-viscous. It should be incompressible. Next, there will be no any effect of changing height on gravity. So gravity will remain constant. And in this entire system, energy should be conserved. So first, liquid should be non-viscous, incompressible. Next, gravity should be constant. It will be unaffected by changing height. And third, energy should be conserved. So the question is, how will liquid flow from some lower level to some higher level? So you must need some external agency to move this entire liquid from lower height to some other higher height. So to avail this, let's say a pressure or external pressure is applied at this point P1 and at this point P2. This pressure difference will do some work on this entire system, which results in change in kinetic energy and potential energy according to work energy theorem. So we can write work done due to pressure difference. Work done equals to force times displacement. Force is net pressure into area of cross section times displacement. Area of cross section times displacement is volume, and net pressure is P1 minus P2 times V. So this will be our expression for work done by this pressure difference on this liquid. Now, according to work energy theorem, we can write according to work energy theorem, net work done by any external agency will result in change in kinetic energy plus change in potential energy. Now just put the value of each term. Work done is P1 minus P2 times volume. Kinetic energy is half mv square. So change in kinetic energy will be half mv2 square minus half mv1 square plus change in potential energy mg h2 minus h1. Samira, any doubt?
No, sir.
Now move this volume to right side. So it will become P1 minus P2 equals to half mass divided by volume times V2 square minus V1 square. Mass divided by volume times gravity H2 minus H1. Mass divided by volume will be density. Mass divided by volume will be density. So we may write it as half rho V2 square minus half rho V1 square plus rho G H2 minus rho G H1 equals to P1 minus P2. Now just rearrange this entire equation which having same subscript to one side. So we can write P1 plus half rho V1 square plus rho G H1 equals to P2 plus half rho V2 square plus rho G H2. In both sides, we have same quantity. There is only change in subscript. Therefore, we can write P plus half rho v square plus rho gh at any instant for the flow of liquid is constant. Yusra, any doubt?
No, sir.
Krishna, is it clear?
Yes, sir, it's clear.
So in this expression, first term will be pressure, second term will be kinetic energy divided by volume, and third term will be potential energy divided by volume. So sum of these three quantity at any instant for the flow in a tube is always constant. Just write it down.
Done, sir.
Sir, can you scroll down? Done, sir.
Done, sir.
Now, in this particular relation, let's say in third part or in this entire equation, P will be variable, velocity will be variable, and H will be variable. Rho, that is density of liquid, it will be constant, and G, gravity, it will be also constant. So we can rearrange this particular equation in some other way as divide this entire equation by rho times G. So it will become P divided by rho times G plus rho times V square by 2 times rho into G plus rho GH divided by rho G equals to some constant divided by rho times G. So constant divided by any another constant will remain constant. So you're left with P divided by rho times gravity, V squared divided by 2 times gravity, and it will be just H equals to some other constant. Now this term, pressure by density into gravity, is called pressure head. The second term, velocity squared by 2 times gravity, is called velocity head. And this third term, only H, is called gravity head. So sum of these three quantity at any instant will be also constant. Why it is called head? It is simply because we can define these particular quantity at any instant for that particular flow. Is it clear?
Yes, sir.
Just write it down.
Done, sir.
Done, sir.
Done, sir.
Find velocity of water in a tube for which gravity head will be 20 centimeter. We have to calculate velocity of water for which it is equivalent to gravity head of 20 centimeter. So just equate these two terms to find B. Samara, what will be your unit? We can equate V squared by 2 times of gravity equals to H. So V equals to 2gh root under 2, gravity is 10, and height is just 20 centimeter. So it will be 0.2 root under. So it will be 2 into 2, 4, and root, it will be 2 meter per second. Is it clear? Samira,
Yes, sir.
Krishna, any doubt?
No, sir.
Okay. Now there is various application of this particular Bernoulli's principle. First is Magnus effect. Suppose you have a ball which is projected horizontally without spinning. So it may attain this path, parabolic path, to hit the ground at this instant. Let's say this is horizontal line or ground. Now, if it is projected by spinning, let's say in clockwise direction, like this. So will there be any effect in its path while spinning in clockwise direction or in anti-clockwise direction? Krishna? Any guess?
Sir, can you repeat, sir, what you said?
Suppose this ball is initially projected without spinning, so it may follow this projectile path or trajectory. Now, if it is projected in clockwise spinning, so will there be any change in its path, or it will remain follow this entire same path? On spinning in clockwise or anti-clockwise, there will be change in path or trajectory. Let me define you how it will be. Suppose this body is projected horizontally, so air around it must be in opposite of its motion. Similarly, at this point, it will be along this direction. So this is movement of air at this instant. Now for the upper part, velocity of particle is in clockwise direction and velocity of air at this point is in anti-clockwise direction. Since these two velocities in opposite direction, so it will tend to decrease the velocity of this particle at the uppermost point. So velocity of particle at this uppermost point will get decreased. Suppose in bottommost point, since velocity of spinning ball and velocity of air both is in same direction, so they will add up or it will tend to increase its velocity. So velocity will increase. So Myra, is it clear?
Yes, sir.
Now, according to Bernoulli's principle, pressure plus half times rho v squared plus rho gh is constant at any instant for the flow of liquid. Let's say height is constant for this particular ball. So there will be change in velocity and correspondingly pressure will change. At upper point, let's say this upper point, velocity is decreasing. So if one of the quantity is decreasing, other must be increasing so that the sum of these two terms at this upper end must be conserved or constant. So due to decreasing velocity, pressure get increased, and due to increasing velocity at this bottom, pressure will get decreased. Krishna, is it clear?
Yes, sir.
Now, due to pressure difference, matter moves from higher pressure to lower pressure. In this part, due to change in velocity, there is change in pressure. Upper end having greater pressure as compared to lower end. So due to this pressure difference, it will tend to move this particular ball towards downward direction. So it may follow this trajectory to hit the ground at this point. So this will be when clockwise spinning. Is it clear?
Yes, sir.
Aisha, any doubt?
No, sir.
Similarly, if the ball will projected in anti-clockwise direction, so it may follow this path to hit the ground at this point. So this will be in case of anti-clockwise. And this middle part, no spinning. Just write it down. This effect, due to which there is change in trajectory, is called Magnus effect.
Done, sir.
Aisha, you have written?
Yes, sir.
Okay. Now let me define you an experiment. Suppose take a paper like this, enfold it from bottom side like this. Now just blow air on this particular path along this direction. In which direction this enfold part move? In downward direction or in upward direction? Samira? Suppose you have a paper strip in which I have just enfold some of its end like this. And air is passed over it along this direction with some velocity v. So in which direction do you think this enfold paper will move? Towards downward or towards upward? Krishna, any idea?
No, sir. So I think it will move downwards.
Just take piece of paper and enfold it from downward direction and blow air from its top surface like this. Let me define you the principle behind it. This blowing air along its horizontal surface towards its top face will increase velocity of this point. And on increasing velocity, pressure will get decreased. Is it clear?
Yes, sir.
Now, this decrease in pressure will tend to bring this enfold paper to move in upward direction like this. Is it clear? Samira, any doubt?
Yes, sir.
So can you explain again?
Suppose air is blown over this particular surface from its top side. So blowing air will have some larger velocity as compared to air at this bottom point. So due to increase in velocity, pressure at this topmost point will get decreased as compared to this bottom point. So there will be some pressure difference between bottom and top surface. So pressure in this case will be larger in bottom point as compared to this top surface. This pressure difference will tend to move this enfold paper to move upward. So it will move towards upward direction. Is it clear?
Yes, sir.
Due to this effect, we can define takeoff of aeroplane. Suppose airplane is moving horizontally on runway with some velocity v. Due to its movement, incoming air will move along its curvature like this, from its top surface, but from the bottom end, it may hit on this particular surface and may get stopped. Due to these two different behavior, velocity at this top end will increase and velocity at this bottom end will get decreased and it will tend to zero. Samira, towards which side pressure will get increased or decreased?
Decrease through upper side and increase to downward side.
Good. So on increasing velocity, pressure will get decreased, and on decreasing velocity, pressure will get increased. Now, there is pressure difference between bottom end and upper end. This pressure difference will be enough to uphold or uplift this entire plane into air. Now, let me calculate this entire term mathematically. Let's say this is first end and this is second end. So according to Bernoulli's principle, we can write P1 plus half times rho V1 square rho G H1 equals to P2 plus half rho V2 square plus rho G H2. As there is no much change in height between these two levels, so this term and this term will get cancelled out. So move this P2 to left side and this term to right side. So it will be P1 minus P2 equals to half rho V2 square minus V1 square. Now this pressure difference will be capable of uplifting this entire system. So pressure equals to force by area, and force will be due to entire mass of the system. So pressure equals to force, that will be mg, divided by area of span or wingspan or surface. So let's say A equals to rho by 2. We can write this particular expression, since it is V2 square minus V1 square, as V2 plus V1 times V2 minus V1. According to A square minus B square equals to A square plus B, A plus B, A minus B. Now, this particular term, V1 plus V2 divided by 2 will be average velocity. So we can write it as V average times delta V. So you'll have to calculate change in velocity between lower end and upper end in this entire motion, which will be capable of uplifting this system. So change in velocity will be equals to mg divided by rho a v average. Yusra, is it clear?
Yes, sir.
Samaira, any doubt?
No, sir.
Okay, just write it down.
Done, sir.
Done, sir.
Krishna, you have written?
Yes, sir. Done.
Okay. A plane moving at 900 km per hour, having total mass of 2 into 10 to the power 3 kg. Find difference in velocity between lower and upper surface to uplift it if area of wing span is 25 meters squared. Density of air is 1.3 kg per meter cube. Just put all the values in the above formula, take gravity to be 10 and simplify it. We have velocity. Take it as average velocity as 900 kilometer per hour. So just multiply it by 5 by 18 to convert it into meter per second. So it will be 250 meter per second. Mass of entire system is 20 to 10 to the power 3 kg. Area of wingspan is 25 meters square. So according to formula, delta V equals to m times g divided by rho A V average. Krishna, you got any answer?
Yes, about to find it, sir.
Okay. It will be about 2.46 meter per second. Samira, you got this answer?
No, sir.
Is it clear to you all?
Yes,
Yes,
sir.
sir.
Okay. So let's stop here for today. I've just left you one part of this particular Bernoulli's principle, that is torsional law, which I will define in next class. And then we'll start new chapter, that is thermal properties of matter. Okay. So just revise this entire part and try to do more and more problem related.